Hello, welcome back to the channel and welcome back to this series on gradients. So in our previous episode I looked at finding the gradient of a straight line from the graph and from the equation. Today we're going to look at finding the gradient of a curve which has a continuously changing gradient, something like this example on the board, so a non-linear or non-straight graph, and we'll also be looking about how to find the gradient at any point on this graph from the equation, which will also introduce differentiation as well, which is a technique that you get to start covering in the UK at AS level, which is the first year of A-Level, and is the technique for actually finding the gradient of a line from an equation. So just to recap from last week, because this is going to be useful today, we said that the gradient is sometimes given the letter m to denote itself, and it is the change in the y position divided by the change in the x position, so that's y2 minus y1 over x2 minus x1, and you can denote the word change by using the Greek letter delta, which is the triangle, so you've got delta y over delta x. And I've got a little bit more on the side, which I'll come to later. So on the board, I have a graph of y equals x squared plus 1. So as you can see, it's a quadratic graph, so it's U-shaped, and every point along the x-axis, the gradient is changing. So it's negative here, getting less steep, and then it gets steeper and steeper and goes as it goes positive. So how do we find the gradient of a graph from the graph? So the way they teach you to do it in GCSE is to draw a tangent at a point. So the way you do this is you find the point where you want to find the gradient. Let's say it's this point here. You go up to the graph, which is there, and what you do is you draw a straight line, or a tangent, which just brushes the graph at that point. And what you do then is find the gradient of the graph. So you then read down to your x-axis, along to your y-axis at one point, and then you also go to your tangent line somewhere else and measure it there. So now you have your y2 value here, your y1 value here, x1 is there, and x2 is there. And you can now apply this to this formula and find your gradient. So there are some massive drawbacks to this technique. As you can see, trying to draw a straight line that just touches the graph is very subjective and requires some skill to do, which obviously I displayed here that I do not have. So that's the first drawback, is how do you draw your tangent. Secondly, does your scale on your graph actually allow you to accurately go across to precisely measure an x2 and x1 value, or do you have to sort of guess it or round it up or round it down? So again, that would induce error in your tangent gradient. And finally, you need the graph to actually be plotted well or made well. So I've drawn this freehand. It's not a perfect graph, hence why I'm not going to actually use this tangent here to do the calculation, because it would be meaningless, because I've just drawn this graph freehand, so it's not produced well. So you need an accurate graph as well, in which case you need to plot it on a computer, in which case if you're trying to find the gradient, you might as well, and you don't know any of these techniques, you might as well look for a program that does give that gradient. So that's the way that we can find the gradient of a curve. We draw a tangent. So I'm just going to point out a general thing about this graph, or an observation. At this point here, the gradient, so if I go here, the gradient m is equal to 0, because this is what's known as the stationary point and the turning point. So it's actually, the gradient has become less steep, it's going to level off and then start getting steeper as we go onto the positive side of the x-axis. So the gradient here is 0, And therefore, if I drew my tangent, it would actually just be a straight line which is parallel with the x-axis. So the reason why I've done this is because I'm going to use this to help find the gradient of this line, or demonstrate how you find the gradient of a curve from the equation. So, how do we find a gradient if we just have the equation? So, let's say I wanted to find the gradient at point 0. What I can do is put 0 into this equation. So, let x equal 0, therefore y is equal to 0 squared, which is 0, minus 1, which is 1. So this is my y value. And let me now just put something else in. Let's change this to x1 and this to y2. Now if I take another point where just beyond this x coordinate, the 0x coordinate, and calculate y there. So I'm going to let it say equal to 1. So let x equal 1. I'm going to call this x2. Therefore, that should be a 1 there. So y2 is equal to 1 squared is 1 minus 1 is 0. So this would give, if I put it into my equation now, y2 is 0 minus 1 all over x2, which is 1 minus 0. So that equals to 1 over 1, which is equal to 1. So you can see that's not equal to 0. It's an approximation of the gradient. So doing this method of just trying to find a little bit further on the graph does give an approximation of the gradient, but it's not perfect. So the question you might ask is, well, why did you go to 1? Why didn't you make your x2 value much closer, say 0.5, 0.1, 0.01? And yes, that is a good way of actually improving the gradient that you actually are trying to calculate. However, there is a better way of doing it than that, which is where differentiation comes into. So I'm going to work this out, and I'm just going to return to this up here. So from that example, we said try and make that point of x2 much closer to the original value of x. So if I go back to this gradient, we've got the change in y over the change in x. If we make that change in y very small, almost indefinably small, we can change the delta to a d. And the same for the x. The corresponding change in x is going to be very small as well. So we can have dx. So this gives dy by dx, is also known as the gradient. And this is how it's referred to in differentiation. So what I'm going to do now is, let's say you wanted to evaluate this at that little bit further on than x. What we have is, we change this x to x plus dx. So that's that little point a tiny bit further on than the x-axis. So that will be now squared because we're just replacing this x term with x plus dx. The minus stays where it is. So what does this do to our y value? Well, our y value is going to go up a tiny amount as well, because the assumption is that our function is such that a very small change in x is going to also produce a very small change in y. So we can change this to y plus dy. So I now have this equation, and what I'm going to do is multiply out this x bracket. So I'm going to have x squared plus 2x dx plus dx squared minus the 1. Right, now what I'm going to show you here is, can you see that the bits I'm going to circle in red is equal to y. So we've got x squared minus 1 is equal to y. We've got that written above. can you also see that this, I'll do this in blue, this dx squared, if the dx is very, very small, this dx squared is going to become even smaller. It's going to be basically insignificant. So this is roughly equal to 0. So we now have y plus, that should be dy up there, dy is equal to, I'll do this in red, so we got y plus 2x dx, and this term is going to be equal to 0 plus 0, so we can cancel out 0, it doesn't mean anything. We can also cancel out this red y with this green y over here, and now we have dy is equal to 2x dx. So I'm going to write this over here. So we've got dy is equal to 2x dx, and I can now rearrange this to be dy by dx, which we know is the gradient, is equal to 2x. So now we have a formula for the gradient that allows us to calculate the gradient for any value of x we put in. So for this point here, we said that we know that x is equal to 0 at the turning point, because of the way this graph is set up. And so now, if I put 0 into this, we have 2 times 0, which is 0, which is our gradient. If I wanted to find my gradient at x equals 1, I put 1 into this, so my gradient here is equal to 2. If I want to find my gradient on this side of the graph at -1, this graph is symmetric, so it should be the same value of the gradient, but there should be a minus sign in front of it. So if I put 2 times -1, that's minus 2, so our gradient here is -2, and that corresponds to the positive gradient on the other side. So this is basically the introduction to differentiation. What we do is we evaluate this function at a point which is a little bit further on than x. So we evaluate it at x plus dx, and we look and we set the y to be in y plus dy. So to cover more of differentiation in the next video in this series. So hopefully you found that useful, and it explains a bit about where differentiation comes from and how your gradients of graphs can be calculated. Please subscribe to the channel to keep up to date, and I'll see you again soon.